Well, I'm very pleased to be with you today. My name is Sean McBride. I am the program coordinator for industrial cybersecurity at Idaho State University, and pleased to be able to speak with this fantastic gathering. My topic today is developing the next industrial cybersecurity workforce. And to get us started off, I want to tell you about a fantastic mountain bike ride in Idaho, and that's called the Route of the Hiawatha. Now, about 2017, I took my family on a trip to northern Idaho, and we did this fantastic trail. It's a 1.6% downhill grade, so it's all downhill. At the top of the trail, you start through a 1.5 mile tunnel, pitch black. You've got to bring your own lights to make it through that tunnel safely. And then you're treated to about 10 fantastic trestle bridges like the one you see in this image. And it was an unforgettable experience. And if you're ever in northern Idaho, highly recommend that enjoyable mountain bike ride. The reason that I start off with that story is we're trying to bridge a gap or connect two disparate domains when we're trying to develop an industrial cybersecurity workforce. And so I want to tell you where this divide that we're trying to bridge came from. And in about 1968, when Richard Morley, who is the American father of the programmable logic controller, invented the PLC, he'd been working with microcomputers, which are much larger, of course, than computers today. But he was frustrated with the moving parts of computers and had an idea for a controller that had no or very limited moving parts and could be programmed in a repeatable way. And so the device you see there on the left is the Modicon 184, an early PLC. Now that market has grown from this first device, if you will, to 175 billion industrial automation market worldwide. Now, when Richard Morley, when people would talk about his invention, he was adamant that it was not a computer. And the anecdotes are that if the word computer were written on a chalkboard, he would erase it. Or if it appeared in a piece of paper describing his product, he would throw it away or rip it up. And so that marks this moment when industrial automation diverged from mainstream computing. And as a result, cybersecurity, computer security was never part of the engineering process for these devices. And I imagine most of you are familiar, or at least have an idea that that's the case. Now, the other image on the slide here is of these Pepperell and Fuchs sensors, right? So other point I need to make is that these Modicon PLCs were originally programmed with this Modbus protocol. And I said that these were invented in 1968. Well, it wasn't until about 2004 when the IEC made Modbus TCP an officially recognized protocol. And so that marks that 1968 marks the divergence, and maybe 2004 marks the reconvergence of these technologies. Now, back to the Pepperell and Fuchs image on the right hand of your slides, we're now seeing Ethernet not only to the PLC, but all the way to the sensor. And so what I'm telling you is these two worlds have come crashing and colliding back together. And we need to essentially build a bridge, a way to create professionals who can operate on both sides of this device, or this divide rather. And thinking back to my experience on the Hiawatha Trail, it's amazing that when that original was a rail line was built, the level and the smoothness and the 1.6% grade of the entire railroad bed and the drilling that had to occur through the tunnels and the bridges that had to be built, it was a massive effort to link two locations together through this challenging terrain. And that's what we're facing today. So when you think about information systems, cyber, maybe that's AV and hardening, but on the other extreme, we've got security process hazard assessment and engineered fail-safes. And we've got to begin thinking how we take people. And when I say people, I mean, let's start with high schoolers. How are we going to prepare them to engineer or design or defend these critical systems? All right, so I mentioned before that I I don't know if I mentioned this. I mentioned that I was the program coordinator at Idaho State University for the Industrial Cybersecurity Program. And interestingly enough, I started this job full time the same year that I went on that trip to the Hiawatha Trail. So it's almost been 5 years now. And when you start a program or when you start teaching, the advice that you're given is to start with the standards. Go look at what the experts say you should be teaching. And there are great curricular guidance standards out there for cybersecurity in general. And I started looking through those standards and wondering, well, what is it from these standards that we need to be teaching? Is there a standard out there that meets our needs? And so I looked at these 8 different standards that you can see on this slide. And I won't take the time to tell you about all of them, but on the upper left-hand side, we've got the Department of Labor competency model for industrial automation. And there's a cybersecurity portion of that. On the second from the left on the bottom is the CSEC 17 curricular guidance, which is probably the most established document for telling cybersecurity instructors, not industrial cybersecurity instructors, what they should be covering. In that CSEC 17 document, there is no reference whatsoever to industrial control systems. So looking across these documents, I asked myself, what would a foundational standard include, right? So going back to our analogy of the bridge or of that rail line that was being built, what do we want that to look like? If we want people to travel this, how wide do we want it to be? What is the depth of the canyons that we've got to cross? What is the depth of the mountains that we've got to drill through? So these are the requirements that I would expect to see in a sound foundation for industrial cybersecurity curriculum guidance. So it's got to address industrial cyber. It's got to make clear that industrial cyber is different. There has to be based on consensus. So a broad number of people, and I would say that's got to be 100 or more, have to have come together to create the advice. Participants have to be qualified. We've got to understand where these people are coming from. It's got to be publicly available. If we wanted to make it widely accessible, then it's got to be publicly available. It needs to include knowledge. It has to describe why that knowledge is included. It needs to include tasks. What things do we want these people to be able to do? And it needs to be able to be extensible so that it can apply to various sectors. And finally, we've got to have evidence that it works in real life, empirical validation of the content. All right, so I mentioned the 8 documents. What we did is we scored the 8 documents. So we just did a simple yes, no, or unknown scoring, where a yes received a 1, a no received a 0, and an unknown or partial received a 0.5. Okay, and so you can see here that the best document that we found was a document put out, it's actually a series of documents put out by the Pacific Northwest National Laboratory. And you can see that of the 11 criteria that we were missing on a bunch of them. So we sat down, myself and colleagues at the Idaho National Laboratory, and said, how can we build this firm foundation that can allow us to bridge the gap? We got together and we said, well, let's create a community of practice, not a community of interest, a community of practice of people who want to solve and address this problem. And I hope that as I've described the current situation, that you find yourself thinking, well, that's me. I want to go ride that trail. I want to be part of this community of practice that can help us develop those next generation industrial cybersecurity professionals who can cross that divide. What we did is we came up with a prototype straw man guidance document, and you can actually download this at the Community of Practice website. We sat down with subject matter experts, 15 of them, and we did some brainstorming. And we went back and we did a second round of not brainstorming, but focus sessions with individuals with different types of experience in industrial cybersecurity. And so that's the process that led us to this document, Building an Industrial Cybersecurity Workforce, a Manager's Guide. Now, let me describe what the document includes. It's got knowledge in these categories: industrial operations, instrumentation control, equipment, communication, safety, and regulation. And as I mentioned those categories, maybe you're thinking, it sounds pretty good, but I would organize it in this other way. And we hope you have those thoughts. We recognize this was an initial effort that should be improved upon. Then as you look at the other half, it's, well, what's the cybersecurity knowledge, right? Industrial knowledge, cybersecurity knowledge, these two things have to come together. And the categories that you see on the right are the categories of the CSEC 17 guidance, right? So we're trying to add these two things together. Now, once we had the straw man for the knowledge built out, we said, what are the roles that need to exist? And when we talk about roles, we recognize that different organizations have different needs and different job titles and different HR approaches. So we came up with this idea of archetype roles, and we identified, I think we identified 7, but we chose to focus on these 5, which we thought were the most interesting. So a manager, an engineer, a technician, analyst, and a researcher. And the concept here was that the breakdown between these would be simple enough that if you were trying to describe the career field and the options available to a high school student, that they would be able to differentiate between a manager and a technician. So we went for that right level of differentiation in our straw man. Then, as I said, we sat down with 2 or 3 subject matter experts who had experience. And of course, we asked them about their experience to qualify them as subject matter experts, and asked them to do a cognitive job task analysis, essentially. So what are the key tasks that someone with this job title would do? And we came up with roughly 1 sheet, which you can see here on the slide, describing the tasks for each job role. And so I highly recommend going and downloading this document and taking a look through it and seeing whether it resonates with you. For our initial cut, we think we did a pretty good job, but we recognize that it needs to be improved. And as I said, we involved about 30 people in creating that straw man. So we want to have a broad consensus. And in order to do that, we want to get several hundred people, or at least nearly 200 people, to participate in the survey. I jumped ahead of myself a little bit. So to get that consensus, first we did the focus sessions, then we created a survey to see how a broader cross-section of individuals thought about the results. So we created that. Now you're getting to the survey. So myself, ISU, colleagues from Idaho National Laboratory, and colleagues from the International Society of Automation created and vetted the survey. It's a Qualtrics survey. It has about 220 questions. So depending on what answers that someone gives, they could spend maybe an hour giving the responses. If they were confident in their response, they could probably get through it in 20 minutes. The core idea here, as I said, was to build consensus. And the voices that have not previously, the first section of the survey asks deep questions about a participant's history, work history, and professional experience. And what excited us about their responses they started to come in, and especially because we distributed this through the ISA, is we got people who previously had not been involved in curriculum development efforts, that their voices were not being heard through documents like CSEC 17, as good as that document is for general cybersecurity. And so if you look at the graph on the top, you'll see that one of the questions we asked is, do you have a professional engineer license. And interestingly enough, of the 166 respondents who had taken this, when I put together, now we hope to get some more, of course, but 166 respondents who had taken this, when I put together the slides, about 37 of those said they had a professional engineering license. And so we're excited to get that type of engineering view on the problem. Now look at the second graph on the bottom, where we ask the breadth of industries that our respondents have experience in. This is fantastic. Chemical and petroleum, maybe you would anticipate that. And then power. So we're getting those two big, important, notable sections. But also look down there at water, wastewater, food and pharmaceuticals, building automation. So we're bringing together a cross-section of people to look at the problem who've previously not looked at it. And what we intend to do is make all of the data publicly available, so that if someone wants to come along and say, hey, how did you guys come up with this answer, this recommendation, we can point to the data. And this goes beyond what previous curricular guidance efforts have done, is they haven't made that data publicly available. So we intend, going back to our analogy of building this rail line, if you will, we intend to make that super smooth and make sure that it's 1.6%, and make sure that if someone wants to build on that foundation, that they can and do so with confidence. Okay, so what are the results going to do? Well, they're going to allow high school teachers, associate degree teachers, bachelor's teachers, graduate teachers to have confidence in the curriculum and to create pathways that make sense. And then what we hope happens, and we're looking ahead, right? When the folks who build that rail line in northern Idaho, they may not have envisioned thousands of people riding their mountain bikes on it one day. We want to look forward to the future and say, well, how are these graduates going to go out there and get real world experience, and then give additional advice, serve as advisory committee members to improve these programs continuously? Let me give you two examples. So what we're doing here at Idaho State University, and I know there are a couple of other schools who are thinking about this model, is we have a technical college inside of our university. So we do associate degrees, hands-on degrees. Students can come through civil engineering technology. They can do on-site diesel power. They can do instrumentation engineering technology, electrical engineering technology, mechanical engineering technology, nuclear operations. We will take technicians, people with 2-year hands-on degrees, and maybe they've been out in the field and want to have a pathway to a bachelor degree, or maybe they graduated with an associate degree and want to do more school. Right now, we have a pathway for them to obtain a bachelor degree. So we'll layer on a year of industrial cybersecurity, and you can see on the slide a listing of rough course titles, and then we point them to a year of management type courses that complement those cybersecurity and technical courses that they had in years 1 and 2. So for example, technical writing, project management, production, supply chain management. So those are the sorts of courses that we recommend students take to end up with a bachelor's of applied science in cyber physical systems. So really exciting pathway. We've had several students at ISU take advantage of this, and about 7 right now who are transitioning to the bachelor portion of that program. Okay, so that is one sort of pathway, right, that this input is going to allow us to create and ideally roll out, not only at ISU, but in other institutions across the country and the world. So the second example that I will give you is an apprenticeship program. So here, again, I'm using ISU as an example because that's where I am, but there are other people thinking about this. Siemens Energy, large energy provider in lots of power plants, their equipment in North America and throughout the world, said, hey, we recognize that to create an a competent industrial cybersecurity professional, it may take 10 or 15 years. And so we want to cut that down to like 4 or 5 years, if possible. And based on their experience I'm speaking for them a little bit here, certainly I'd be happy to introduce you to the Siemens people, but based on their experience and success with other apprenticeship programs or programs in other industrial fields, they said, let's build an industrial cybersecurity apprenticeship relying on the current curriculum of Idaho State University. So students will graduate from high school and then be able to go work for Siemens for 4 years as full-time employees, starting with half of their target salary, and take our industrial cybersecurity program as the classroom learning component associated with the apprenticeship, and then come out after 4 years with an associate degree in industrial cybersecurity, but also 4 years of full-time experience. And we are so excited about that concept of accelerating our rate of production of these individuals who are capable, in the end, of bridging that gap. So my invitation to you is to join the industrial cybersecurity community of practice. And I have the link in the slide there. It's fairly easy to remember, inl.gov/ICSCOP. We meet, there's 2 subgroups, one dealing with workforce and one dealing with curriculum. We meet monthly in each of those groups. And then we have 2 semi-annual workshop events where everyone meets together. So please come and join us. We'd love to have your input. So that concludes my presentation, and I hope that you continue watching and enjoying the great content that Accenture is putting together for us.